All right. Love those redox reactions, huh? Pretty good, fun stuff, yes. All right, now we're going to move on into the next unit of this electrochemistry topic, and it's called Galvanic Cells. I loaded in a video for you, Khan Academy. Khan, my buddy Sal, does a good job. A little slow, but does a good job. It's a very good video on what a galvanic cell is. Now, that bottom line, a galvanic, sometimes called a voltaic, sometimes called an electrochemical cell, is essentially a battery. It's a wet cell battery. Wet cell battery, yeah, your automobile has a wet cell battery in it, meaning that what's called wet because it's a solution. So if you were to take your automobile battery and open it up, don't do this. It's got sulfuric acid in it, nasty stuff, but it's a solution, and therefore a wet cell battery as opposed to a dry cell battery. A dry cell battery would be like this bad Larry right here. This is a battery. I just took the outside cover off it, but this is the dry cell battery. It's dry because if you open this up, there's like pasty stuff. It's not a solution in here, not a water solution. Sometimes you can see the pasty stuff come out. When batteries get old, they'll kind of have that white, crusty stuff come out. That is a dry cell battery. But they're both batteries, and what they do, they produce energy / power in order to power up our devices. I mean, we're all addicted to our cell phones now, especially you younger kids with your Snap Face and Twitch chat and whatever you're using all the time on them. Okay, you're like, those things are like part of you. You're addicted to them. So you need this electrochemical cell to function so you can keep using your addicted device. Okay, so a galvanic cell, a battery, has certain parts to it. You watch the video, you've got two metals. That's what we've got going on here. We've got two different metals. In the video, I believe they had zinc and copper, which are very common metals. They make batteries, zinc and copper. And they also have something called a salt bridge, which allows a circuit to flow. So if you watch that video, you could see that electrons were moving from one metal to another. Now we have to figure out why those metals would move, why the electrons would move from one metal to another. Which direction would the electrons move? In other words, oxidation reduction. Who's going to be undergoing oxidation with these two metals, and who would be undergoing reduction? We need to know that, and then we need to figure out how much current and how much voltage would be produced. Batteries produce voltage. This is a typical D-cell battery. It produces 1.5 volts of electricity. Okay, you know, you've heard of voltage before. Car batteries are 12 volts. Household circuits are 120 volts. It's a lot more. So this voltage has something to do with potential energy, something to do with electrical potential energy and the ability to do work and get jobs done. Power your calculator, power your clicker thing for the TV, power your cell phone. You need voltage to do that. And so what we're going to do today is figure out how much voltage a cell can produce. Now, the chemist says, hey, we got that job. Our job is to figure out what batteries work, how much they produce, and then you physicists people and engineers, you can take that energy and go make stuff with it. Okay, so our job is to figure out how much voltage can be produced with these batteries, hence galvanic cell. All right, now, so let's dive in. You're going to need your tool of equipment. It's actually not the periodic table. In chemistry, always using the periodic table is our tool that we need with us all the time. What you need is what's called a standard reduction potential table. Now, I have made a copy of one. This is a terrible copy, but it's the only one I have with me, so I'm going to use this one. But you can see it's kind of bleh. I'm going to take a picture of the one in the book, and I'll upload that, so you get a better copy of it. You need this copy in order to do what we're going to be doing today. And this standard reduction potential table, and this is out of an older version of Chain Chemistry, 11th edition, but they all have it. Again, remember, those editions never change. All they do is change a few photos, for crying out loud. Out of the chapter on electrochemistry, chapter 18, you will find this, and you're going to need it. This is going to be like your little Bible, for lack of a better example, that you're going to have to get you through this. All right, so I'll explain how this works. We need to know how it works shortly. Okay, let's take a look at our problems. We have gone through the redox reactions. We have problems 2 through 7. Well, that's a lot of problems. Some of these problems don't take very long, so don't be panicking out there. Don't panicking. Problem 2. Calculate the standard EMF. Now, what the heck does that mean? First 4 words, I'm confused. Calculate the standard EMF. EMF is electromotive force. It's another way of saying voltage. Okay, there's many words that mean the same thing, and electromotive force, voltage, electric potential, potential difference, all those words mean voltage. We're just thinking of that as voltage, but it's the way it's written. It's like an old school way of saying voltage, but it's still around. Calculate the standard voltage of a cell, battery, that uses silver and aluminum to produce this voltage, to have this oxidation reduction reaction that go on to produce a current and therefore allow us to do work and produce that voltage to do that work. So it says half cell reactions. Remember when we did the redox reactions, we have half cell reactions, meaning something becomes oxidized, something becomes reduced. That's what that means. One of these two metals, silver or aluminum, will become oxidized and one will become reduced when placed together in a cell or a battery, galvanic cell. Well, how am I supposed to know who gets oxidized and who gets reduced? If you have actually some knowledge of the periodic table and electronegativities, you could figure this out. So I'll kind of mention that a little bit in just a bit, but you can actually figure out who is more likely to become oxidized and who would be reduced. Or, instead of thinking about electronegativities and periodic table placement, we can use that sweet table I was just showing you. This table, which you all should now be having in front of you, you need it, this is what's called a standard reduction potential. So on this table, it's going to list from top to bottom what elements will become reduced and what elements will become oxidized. This has a lot of the common elements and the different oxidation numbers for those elements. Like copper can have a +2 or +1. Well, copper's on here. Both of those +2 and it's +1. So not every element on the periodic table is on this table here, because that would make it really, really big and long here with all the different oxidation states. But some of the common ones are copper, aluminum, silver, fluorine, chlorine. Some of these very common elements are on here. If they're not on here, we can either look them up on a different table, Googleize them, you can always Google everything, or we can figure out what that element should be if it's not on the table, what value should it be given. We'll do that later. Okay, so how do I use this? Silver and aluminum. Find them on the table. Got it. I got excited. Find them on the table. If I find silver, I see silver about yay far down, about 1/3 down the table. And if I find aluminum, I have to go close to the bottom. Aluminum's down here, silver's up here on the table. Now on here I wrote, and I did write this, and so your little photo of it has this, reduction, oxidation. The higher you are up on the table, the more likely you are to undergo reduction. If you are the higher of the two elements that we're comparing, metals, and it doesn't have to all be metals too, we have nonmetals on here. And there's fluorines at the top. Why is fluorine at the top? Fluorine, let's go through that real quick. Why is fluorine at the top of this table? Fluorine means it's going to be super reduced. It's on the highest part of the reduction table because it gains electrons. Remember the electronegativity of fluorine? Remember? You remember. Upper right corner, highest electronegativity. On a scale of 0 to 4, it's a 4. Can't get any higher than that on that scale. Fluorine grabs electrons. It goes out, gets them, and holds onto them. If you take in electrons, what happens to your oxidation number? It becomes more negative. It goes down. That's reduction. And fluorine is the winner when it comes to grabbing and holding on electrons. It will become reduced. Hence, it's the highest element on the reduction table. It becomes reduced. Okay, down here we have lithium at the bottom. What does that mean? Lithium ain't going to be gaining any electrons, people. No, it's going to be giving them away. That's what that means. You'll become oxidized. Up here, reduced. Down here, oxidized. Now let's go back to our two elements, silver and aluminum. Silver is about here, aluminum is down here. Silver is higher on this chart than aluminum. That means silver, with the silver and aluminum combination, will be the thing that gets reduced. If you're higher on the chart than who we're comparing you to, you get reduced. That's actually pretty easy. The higher up on the chart you are when comparing it to a different element, you get reduced and the other element gets oxidized. Is it possible? So in this case, with silver and aluminum, silver is reduced, aluminum is oxidized. Silver's higher, so it becomes reduced in the combination. Is it possible for aluminum to be, compared to something else that the aluminum could actually become reduced? Yeah, sure. If you're comparing aluminum to beryllium, magnesium, sodium, calcium, strontium, barium, potassium, lithium, it's higher than those. So if it was a comparison between the aluminum and any of those, the aluminum would become reduced and the others below it would become oxidized. So it's a comparison in positions of the two elements you're looking at. Okay? All right. Galvanic cells are going to have two metals. So we're going to always compare two metals in their position on this table. Higher one up, reduced, the lower one oxidized. So in this case, I know the silver becomes reduced because it's higher on the table. So let's take a look at this. Silver and aluminum. Okay. Now, so on the table, silver's higher than aluminum. Now, let's take a look and see what it says on the table for silver. It says, where'd you go, silver? All right, silver positive plus an electron becomes silver solid. So silver ion gaining electron. And remember when we did those redox reactions, when we had a reduction reaction, we always put the electrons on the left of the arrow. So this is a reduction. This is a reduction table. It's showing reduction for everything on here. So everything on here is written as a reduction. The electrons are on the left. Okay, so the aluminum is a positive 3, so we're going to have to gain how many electrons to make it a nice solid aluminum? That's correct, 3 electrons. But don't believe me. Don't believe me. I wear stupid shirts. So look on the table and see if that's what it says. Let's find aluminum and hokey Pete and Joe. Look at that. Yeah, aluminum plus 3 electrons makes aluminum solid. So aluminum atom, non-ion. Aluminum ion plus 3 electrons gives you the aluminum atom. Okay, so what do we got here? We've got 2 reduction reactions written. The electrons are on the left. We have silver higher up on the chart, aluminum lower. And then we're given, also on the chart, it says E with that little zero, that little circle that shows up again. And if we remember, that means standard conditions. So E also is another way of saying voltage. That's the energy. Energy is going to be our voltage. Voltage and energy are not quite exactly the same, but they're going to be, for us, the same. Close enough for government work, so we're going to say they are. Energy and voltage. Voltage is energy. Okay. Under standard conditions, when this reduction happens, I look at the voltage. Let's find that silver again, and there it is. Now, you got to make sure you're reading across there. Positive 0.80. Positive 0.80 is the voltage, okay, that is given off by silver when it gets reduced. With me? Okay. Silver gets reduced, positive 0.8 volts. When aluminum gets reduced, what number goes along with that? Let's find the aluminum again. Negative 1.66. Negative 1.66 volts. Now, why is this a positive, this a negative? And what does this mean? So negative voltage, you get negative voltage out of this? It doesn't make any sense. I thought you'd get voltage. No, if you think about it, it does make sense because the aluminum has to gain 3 electrons to do this, and aluminum does not want to gain electrons. Okay, think and remember that. Aluminum doesn't want to gain electrons, it's to lose them. So if you're going to have aluminum gain, 3 electrons, you're going to have to put energy into the system because it doesn't want to do that. So that negative it means that you need to add energy into the system for this to actually happen. This doesn't want to happen. Remember earlier I said the higher up on the chart you are, the more you want to be reduced. The lower down on the chart you are, the more you want to be oxidized. Aluminum is pretty far down the chart. It wants to become oxidized. It doesn't want to do this. This is a reduction table, so it's showing reductions. It doesn't want to do this. So if you're going to do this to aluminum, you're going to put energy into the system. All right? Okay. Silver will give up that one electron. It's okay with that. Actually, it'll take one. It can also take one as well. We talk about metals as wanting to give away their electrons. That's true, absolutely true. Some want to give them away more than others. And this is kind of a way of showing that on the table. Okay, so here's what we know. This is a lot of babbling. This is a long video for this first problem, but there's a lot of background stuff I have to go over so we can make these other problems go quicker. This is going to get reduced. This is going to get oxidized. This is higher up on the chart. That's why. Okay, so if I know that this gets reduced, I'm going to write what's called the E-cell equation to figure out if we make a battery out of these two metals, a galvanic cell, what will the voltage be produced? Okay, got to remember these numbers. I can go on, let's see. Oh, I have room here. Yeah, I have everything on the bottom. All right, the equation is, and this is on your equation sheet, E for a cell. Remember, E means voltage. The voltage produced by a cell, a battery, a galvanic cell, the voltage produced by a battery under standard conditions. Remember what standard conditions are. They mean under atmospheric conditions, 25 degrees Celsius. Also, since these are solutions, we're talking about galvanic cells being solutions, things floating around in water. We're talking about a 1 molar solution. These are standard conditions mean 1 molar. I'm going to write that down. Standard conditions mean, that's my standard conditions, equals 1 molar solutions at 25 degrees Celsius. Okay, and 1 atmospheric pressure. That's not going to come into play for this, but those are the standard conditions. And the standard amount of voltage or energy produced on this chart is based upon having a 1 molar concentration of these solutions. If we don't have 1 molar, then we're going to have to do something nifty and cool, which of course we will do. Oh, I knew, you knew, yeah, you do, yeah, I knew, you knew. All right, keep going. Let's get this done. Long video, gosh. Okay. The voltage produced by this battery is going to be equal to, or any battery is produced by, is done by, taking the E at the cathode minus the E at the anode. That's the equation you need to do many of these next problems. If you want to figure out the voltage produced by a cell, you need to take the voltage at the cathode and subtract the voltage at the anode. Well, how do I know? One of these is going to be an anode and one is going to be the cathode. How do I know which one? I mean, who's who? Do I just take a shot at it, 50-50? Easy peasy lemon squeezy. Here's how you remember. Anode begins with the letter A. That's a vowel. It is A-E-I-O and or U. A is a vowel. Oxidation begins with an O. That's a vowel. Anode, oxidation. A-O vowels. Remember that. So oxidation occurs at the anode. This is where oxidation occurs. The cathode is where reduction occurs. Is C, cathodes begins with C. Is that a vowel? No, no. Reduction. That begins with an R. Is that a vowel? No, no. Not vowel, they go together. Vowel, vowel, they go together. That's how we know. So we're going to take these numbers here and put them into the proper spot. Okay, so let's do this. You get the voltage of the cell. I take the reduction potential, standard reduction number that occurs at the cathode. That's the reduction. Now, who's undergoing reduction here? The one higher up, that was the silver. Silver's number higher up in the chart is undergoing reduction. The reduction value from that chart goes in the spot for the cathode. 0.8 goes here. 0.8. Minus the value from the reduction chart that goes along with oxidation. If you're lower down, you're getting oxidized. Aluminum gets oxidized. So we subtract negative 1.66. All right, do the math on this. This is going to be adding, so 0.8 minus or adding 1.66. This comes out to be 2.46. 2.46 volts. This is volts, remember. We're calculating the voltage produced by this galvanic cell, this battery, when using these two metals in the battery, in the galvanic cell. So if we're using silver and aluminum, all right, 1 molar solutions, I would expect to produce 2.46 volts out of this galvanic cell. That's pretty good. Remember, this battery is 1.5 volts. It's actually producing almost an entire volt more than our typical 1.5 cell battery. Okay. You might say, well, then if you're producing more voltage, why don't we use make galvanic cells, make batteries out of aluminum and silver? Well, aluminum wouldn't be a bad choice. It's cheap. Silver ain't. Okay, cost effectiveness. So we're using, when it comes to battery technology, you're using things that will easily produce your voltage that you need at a cheap, reasonable cost. So economics comes into play here. But that is how we calculate that first. And I hope that was the question, the answer to the question. Write a cell reaction under standard state conditions. Write the cell reaction that occurs. Okay, I wrote the cell reaction that occurs. Under standard state conditions, we did it. We came out with the voltage that would be produced by this galvanic cell using silver and aluminum. More examples to come. That was a long video. I apologize.